Right. We're looking at redox reactions. It's the last topic for the year. It's the last of your chemical reactions. So we know by now that there's thousands of different chemical reactions that take place every second, naturally, unnaturally. Right? These chemicals, when they react with each other, they react in a very predictable way, allowing us to classify these reactions into different categories. For example, combustion, acid base reactions, and now we're looking at redox reaction. So basically, when I'm looking at redox reaction, I'm looking at reduction and oxidation reactions. And you're going to see me use R, X, and S for the word reactions quite often. And if I look at my key concepts, the first thing we're going to look at redox reactions, we're going to look at all the terminology so that we can understand what these reactions are before we get started. The next thing we're going to look at is what we mean by transfer of electrons. So we're looking at if I have reactants and I'm going to get out of them products. We know that at this point I've got an activation complex where everything will split into its individual atoms and ions and so on. And when that happens, I'm going to end up with my products. All right. So when we look at a direct transfer of electrons, I want to know, how do my reactants go from being compounds or whatever, compounds or molecules, and how do they go into this activation complex zone? And when they get in there, how do they become products at a microscopic level? Then we're going to look at the rules for assigning oxidation numbers. This here, NB. Like how you had to memorize your table of cations and anions from grade 10, at this point, we're going to be giving you these new things which you'll have to also learn off by heart. And then we're going to bring together two things, redox reactions, which we're doing now, and acids and bases, which we've already worked on. Right, so this is the introduction. So you'll notice that when I do this, or these types of videos, I'm going to do them in stages. So I might do a few key concepts at a time, or I might get do examples, but please make sure that you watch them in orders. So this is redox reactions number 1. So we're going to get into the first key concept. Right, we're looking at redox reactions, key concept 1, and we're looking at what is a redox reaction. So if I look at the word redox over here, right, if I look at this word redox, this word is split directly into two pieces. Right? The red part of it is called a reduction, and the ox part is oxidation. So when we talk of a redox reaction, we're talking about a reduction dash oxidation reaction. Now if you can see how it's written together, right? So what that means is, if they're happening like this and it's called redox, it means that in my reaction I've got two parts. So this here and this here, they make up two halves of a whole, right? So that means these reactions are basically happening at the same time. So for a definition, we can say a redox or oxidation reduction reaction is a type of chemical reaction that involves a transfer of electrons between two species. So a redox or oxidation reduction reaction is a type of chemical reaction that involves the transfer of electrons. Right, between two species. So what do we mean by species? Right, a chemical species is a term that refers to a set of atoms, molecules, or ions with the same chemical formula. Right? For example, if I look at something called a thermite reaction, right? Let's have a look at a thermite reaction. Then it's a type of reaction like combustion and so on. If I take iron oxide plus aluminium, I'm going to end up with, that's going to be two iron atoms plus aluminium oxide. Alright, so I started off with iron oxide, ended up with aluminium oxide. So what you'll notice here is that in this reaction there are reactants as well as products. And if we look in these here in this type of reaction, I have 4 species of reactants, or 4 species rather, involved in the reaction, with my reactants being Fe2O3 and aluminium, and my products being Fe and aluminium oxide. So if I have things that have the same chemical formula, then we look at something like this. Right? I can tell there's a reaction happening, or there's transfer of electrons, because we're going to get to that next thing where we look at oxidation numbers. So at this point, you need to understand about redox reactions is that they're everywhere. Your body, let's say your body, right? Your body uses redox to convert food and oxygen, right, into energy plus water plus CO2. So a redox reaction is something like cellular respiration. Right? Another place we see it is in batteries, and we're going to look at that in a little bit of details, in electronics. Right? You'll see that I'm going from chemical to electrical, and in grade 12 we're going to look at this chemical to electrical in a little bit more detail. Alright, so when we talk about these redox reactions in the world around us, they include a wide variety of reactions: burning of fossil fuels, like I said, cellular respiration, we use it in industry, We use it with metallic and non-metallic processes in this oxidation and reduction. So let's look at what we mean by those two concepts. So the first thing we must understand here is that we have two types of reactions. So it's one reaction made up of two halves. Right. The first half of the reaction is called oxidation. And when we look at oxidation, there is a loss of electrons. Now, if I'm losing electrons, if anything loses electrons, so let's say I have an electron here, and it's going to be lost. Goodbye. All right? That means that on the other side, in order for something to lose an electron, there must be something that gains that electron. So that's your second half. Your second half reaction is called reduction. Right? And in reduction, we're going to have a gain of electrons. Right, so whatever the oxidation half of the reaction loses, there must be something to collect it. Now in this situation, we say that it's oxidation that's going to lose, right? However, the area which is gaining is called reduction. So that sounds a little bit off, because if something's gaining, how do we say that it's being reduced? So what we say is that anything that gains electrons, right, is being reduced. And we'll look at that in a little bit more detail as the videos go on. Alright, so another thing, these oxidation, reduction reactions happen simultaneously. Right? Simultaneously means they happen at the same time. Think about it like this. If I think of the conservation of matter, it says matter cannot be created nor destroyed. So what's happening here is, if I have an oxidation which is giving off those electrons, it has to go somewhere, right? Whatever is given off has to go somewhere. You cannot destroy matter. It doesn't just disappear. And we know that from conservation of matter. It means that that reduction half of the formula must take on those electrons. So you cannot have reduction and oxidation reactions happening without each other, right? If I can't have the reduction half gaining electrons out of nothing. So you cannot lose electrons if something doesn't gain the electrons, and vice versa. You can't gain if something's not losing. So according to that conservation of matter idea, we need to understand that these reactions are happening simultaneously. Right, when we come to the transfer of electrons, there are two types of redox reactions, right? The one is called the direct transfer, right? If I'm looking at the direct transfer, we're looking at two substances involved with each other, which have direct contact. Direct contact means things like if I had two chemical substances in a dissolving situation, or if I'm looking at situations where I have displacement, or I have situations where I have ionic substances in water, right? Those would be what we call a direct transfer. It means that those two substances or chemicals are coming into direct contact with each other. Right? The other thing we're looking at is indirect transfer. Oops. Right, when we talk about an indirect transfer, we're looking at reactions in cells or batteries. Right? And what's happening there is we got something called an electrolytic reaction. And in these electrolytic reactions, we have an electron transfer outside the circuit. Alright, so for example, inside my battery, let's say this is my battery, I've got all of these atoms, right? And they react with each other. So I've got an electrolytic reaction happening inside the battery or the cell. When this reaction happens, remember this battery is connected to a cell. So what's going to happen is on this other side, when this reaction happens, it's going to push these electrons out. And when it pushes these electrons in of the conducting wire and creates that kind of a reaction, we're going to have electricity. So inside here, I've got a chemical reaction, right? And in this chemical reaction, we're forcing the electrons. So the electrons are forced to travel in the conducting wire, right? So by doing that, we have an indirect transfer of electrons because they don't originate from the original position of inside of the battery. They start inside of the battery and then we go from chemical into this thing, which is electrical. Right, so those are the two types of transfers that we're looking at. Right, let's have a look here. If I had to look at a direct transfer of electrons, and what I did was in this beaker I put a solution of copper sulfate. It will be better for you to actually draw it out and use pencil or whatever and color that in blue. I had copper sulfate, and what I did was inside of this copper sulfate solution, that strip you see over there is either a zinc metal or an iron metal. Either one of these two. We're going to just look at what would happen. Alright, so what's happening here is if I had to have, let's skip this here. If I had to take zinc, which is a solid, plus copper sulfate, which is a crystal, which is a solid, right? And I put it in a water solution, I'm going to end up with what we call a single displacement. We're going to have Zn, it's going to take out that SO4 plus copper, which is going to be a solid. Right, same thing with the iron. I'm going to take iron, which is a solid, plus copper sulfate. Let's say the copper sulfate is rather aqueous. I'm going to end up with iron sulfate plus copper, which is going to be a solid. Right, so initially when this whole thing starts, these metals will be a silver gray, right? This copper sulfate would be a bright blue, right? However, at the end of this reaction, as you can see in this image here above. What I end up with here, and you can see the color is black. So the metal is not silver gray anymore, it's black. And the solution is not blue anymore, it's now clear. So what you end up with here is you end up with an aqueous solution of zinc sulfate or iron sulfate, which is colorless. And then you end up with a metal, a new metal, which is copper, or rather the color is then black. Now from what we learned in grade 10, there would be an ion exchange. And when we talk about ion exchange, and you've done this recently with the types of reactions, you can see that what's happening is here, that these metals here, iron and zinc, are quite reactive. And they come along, and what they're going to do is, let's say if I look at the iron, for example, even the zinc, okay, let's look at the zinc or the iron. If I have the iron, right, the iron is in a situation now, it's going to come here, where this copper is, it's going to take this whole copper and it's going to push it out, right, and it's going to replace it. So you've seen from single displacement, double displacement reactions. Right, and how this whole thing works is we look at the more reactive metal. So between iron and copper, iron is more reactive. And when iron is more reactive, it's more likely to come to copper and say, listen, move out of the way. I need to make a product. So when we look at metals like iron, or we look at metals like zinc, we know that they're more reactive than copper. So what we can say is that if I had copper, the reason why we use copper for pipes, and we use copper also for electric circuits, it's beneficial to us because copper is not as reactive. And because it's not as reactive, it doesn't react very easily with other things that are around it. Right? So when we're looking at this, it's very easy. It is easy to produce copper out of solutions. So if I want to make copper or extract copper, if I'm not doing it in the mining process, I can get it out of different types of solutions. So I want you to think about it like this. Copper in its raw form, in its copper ore, is blue in color, right? And in order to work with this copper ore, which is blue in color, I don't want that type of thing. I want copper, I want copper metal, because it's easier to work with the metal itself. And what I actually want from the copper metal is I want to extract only what I can use. So I've got this blue crystal, but I want this brownish metal. And the only way to go from here to here is to dissolve this. So dissolve the crystal to extract copper as a metal. Right? That's the only way that I'm going to be able to go from a copper ore into a copper metal. Right? So we're just going to go a little bit deeper into this. Right, so if I'm looking here, I have a situation where I've got zinc, right? A zinc plate. So when they ask you to explain this, a zinc plate is placed in a blue copper sulfate solution, right? The solution, after some time, loses its color, and the zinc is covered with a brownish or blackish precipitate. Right. So eventually the solution becomes clear, and what you end up with is that this thing that loses its color is zinc sulfate. We just discussed that. And this brownish reddish thing is a copper powder, because when we remove the water, you're now left with copper powder, which is a solid metal, and that's how we've extracted it. So if we look at an ionic equation, right, so I'm going to break everything into their specific ions, right? So I'm going to write a balanced equation, and it's called the ionic equation. An ionic equation leaves everything in its individual ions. So if I had to look here, it would be zinc plus copper, Cu2 plus SO4 2 minus will give me zinc 2 plus SO4 2 minus plus Cu. Right. So if I look at this situation here, your zinc, right, let's look at the zinc. If I look at the charge here, it has no charge. But when it became a product, it has a charge of 2 plus. So the zinc goes from no charge to having a 2 plus charge. So how does it go from being neutral, right, it's neutral here, to having 2 plus? The only way it has to do that, it had to lose electrons. And how many did it lose? 2 electrons. So it lost 2 electrons, and it becomes positively charged. So if something loses electrons, right, if something loses electrons, I can say I have oxidation on this side. So therefore, the zinc metal is oxidized. Right, this is just a basic overview. We're going to get into this. Right, the next thing I'm looking at is, oops, let's choose the green here. Right, if I look at the copper started off with a 2 plus charge. Here's it there. But when it moved to the other side, it became neutral. So how do I go from 2 plus to neutral? What had to happen here is that the copper starts off with a charge of 2 plus and becomes neutral. Now to get rid of 2 positive charges, I need to gain electrons. How many am I gaining? 2 electrons. So can you see it's starting to look the same on both sides? Now if I'm gaining electrons, I know that a reduction is taking place here. So the zinc here, right, lost its electrons, and the copper took the electrons. So therefore the copper, right, the copper 2 plus metal, or rather let's say ion, is reduced. Right. Then if I look at the other thing, the last thing there, look at the SO4 on both sides. The SO4 stays SO4. So there's nothing happening. So my relationships are between the zincs and the coppers. So let's say I had to write out these two half reactions, right? So the first one is the oxidation. So the oxidation starts off as zinc, and then it becomes zinc 2 plus 2 electrons. Right, so this is what we call the oxidation half reaction. Right. The second one I have to write out is for the copper. But the copper doesn't start off as copper. It starts off at Cu2 plus. And that Cu2 plus, has to become copper. So plus 2 electrons will lead me to copper. Right. If I just move this whole thing down. And then we call this the reduction half reaction. Right. We'll get more into detail with this, but this is just the basics of what you need to understand about what's happening in these types of reactions. Right. The next thing we need to look at is, like I said, the SO4 2 minus. Right. What I would have noticed is that on the left hand side was equal to the right hand side. I had SO4 2 minus on both sides, and this is an anion. Right. Now notice, number one, it does not participate in the reaction, right? But without it, the reaction cannot take place. Right, so what we mean by spectator ions may be either cations or anions. The ion is unchanged on both sides of the chemical equation and does not affect the equilibrium. We're going to get to what that means in a bit. Right, it says when writing the net ionic equation, spectator ions are found in the original equation are ignored. That's important because we're going to get to that now. Thus, the total ionic reaction is different from the net chemical reaction. Right, so now in this situation that I have, we need the SO4 2 minus, right? Because in the reaction, in this whole situation, I need copper 2 plus. That's what I need, right? And you can't just pick it off the ground, right? You're not going to get copper 2 plus ions or pure just copper, uncharged copper, neutral copper just lying around, right? So in order for us to get that copper out, or to get that copper 2 plus, I need it to become an ion. The only way it's going to become an ion is if it has the potential to bond. And because if these two things makes copper sulfate and it makes a compound, that means that I'm going to be able to extract that copper 2 plus. But what happens is, if I look at the charges here, the SO4 2 minus doesn't change. Each charge stays -2, 2 minus on both sides of the equation. So it's not something that participates. So when we talk about spectator, I want you to think of sports games or sports matches, right? If I think of a football match and it takes place, you are the spectator. You create the vibe in the stadium. You create a fan base, but you don't actually go onto the pitch. But what would be the point of a football match if there's no spectators? And we've seen it now during this COVID time, but all of these football matches that don't amount to anything because you have a situation where there's no fans, so it just feels boring. So these reactions are the same. They don't use this SO4 2 minus, but they need it. So what happens is when we write out these equations, right, you'll notice that it is not included in the half reactions. That's important. It's not included in the half reactions, and it's also not included in the net equation. Right. So when we talk about the situation, when we say I want a net ionic, if I want a net, I want a net ionic equation, right? It's going to be Zn plus Cu2 plus gives me Zn 2 plus copper. Now electron loss and gain must be the same. So in this one it worked out a little bit better because the one lost electrons, 2 electrons, and the other one gained 2 electrons. Alright, so I know that from my 2 reactions I've got those two, and they kind of just cancel each other. So when I put 2 half reactions together, it does not include the spectator ion, and it doesn't include the electrons. But we're going to get into this. Alright, so this would be what we call a net ionic reaction. And if you watch the next video, we're going to look at how do we know whether a reaction is redox if we don't know what the half reactions are. Right, so that will be the next video.